You can't see a planet forming inside a dusty disk, but you can feel it tug. Right now, Gaia is watching young stars twitch ever so slightly.
This is our galaxy, as seen by our Gaia Space Telescope.
And those tiny jitters might be the first clean fingerprints of planets still under construction. In this video, we'll show how swapping light for gravity lets us peek through the dust and catch worlds in the act of being born.
Gaia has also revealed how nearby dwarf galaxies and the large Magellanic Cloud are shaping its evolution.
Stay to learn how astrometry turns a star into a seismograph for its hidden companions, what a wobble actually looks like, and why this could push planet discovery earlier than ever. If newborn planets are being built right now, why do our sharpest images still look like foggy donuts? The short answer is, the nursery is messy. Young stars sit inside thick, rotating disks of gas and dust. Those disks glow in infrared and radio because dust grains warm up and molecules emit at long wavelengths, but they choke off most visible light. Any forming planet is buried under layers of grains, stirred gas, and shadows, so the light we want gets scattered and absorbed before it ever reaches us. You've seen the bright rings and dark gaps that made headlines. They're real, and they're gorgeous, but they're not a confession from a newborn planet. The same patterns can come from the disk itself. Magnetic fields can launch winds that sweep material aside. Fluid instabilities can set off spiral waves that look like wake trails. Even simple chemistry matters. At snowlines where water or CO freezes, grains stick and bounce differently, changing how dust piles up and making ring-like contrasts without a planet at all. It's like trying to spot a fish under muddy water. You notice ripples, swirls, maybe a brief flash, but the fish stays hidden. We can read the surface pattern and guess what swims below, yet the mud keeps us from seeing the body that caused it. Disks do the same thing to our telescopes. We detect structure, not the sculptor. Near-infrared direct imaging goes after the faint glow of young planets, but contrast and resolution bite hard. In star-forming regions around 100 to 150 parsecs away, one astronomical unit on the sky is only a few to several milliarc seconds. That's smaller than what most instruments can cleanly separate from the star's glare. Coronagraphs help by dimming the star, but they don't erase scattered light from the disk itself. Dust grains throw light in all directions, leaving a bright, mottled background. A small, warm planet has to outshine that speckled haze at the right separation, and often it doesn't. Take HL Tau. Its famous ringed disk stunned everyone with dozens of crisp gaps only a few million years into its life. AS-209 shows similar rings and even hints of a localized clump where dust traffic seems jammed. One camp argues for several low-mass planets carving lanes, each tugging nearby material. Another camp shows that if you tweak grain growth, turbulence, and snowlines, you can recreate similar rings without invoking planets at all. Both sides fit parts of the data, which tells you how tricky it is to claim a catch based on ripples alone. Spectroscopic tricks struggle too. Radial velocity looks for Doppler shifts as a star moves toward and away from us, but young stars won't sit still. Star spots rotate in and out of view and fake velocity swings. Flares reshape line profiles. Accretion veiling fills in absorption lines with extra hot continuum, muddying the precise measurements you need. That jitter can be larger than the tug from a small or even moderate planet, so the signal drowns in the star's own weather. So if light-based methods stall in dusty nurseries, what can slip past the fog? The disk can scatter and block photons, but it can't hide mass. The cleanest path might be to stop chasing the planet's glow and instead watch the parent star. If something heavy is orbiting inside that disk, the star won't sit perfectly centered. It will trace a slow, tiny drift on the sky. That's the pivot. Move from photons to force, from brightness to motion. Enter Gaia, turning the star into the sensor by measuring minuscule changes in its position. Those subtle shifts are a gravitational clue that ignores the dust and points straight at the culprit doing the pulling. What does a forming planet sound like to Gaia? Not a flash or a flare, but a slow, steady sway in the star's position. Too tiny to see, yet clear when you measure it with extreme precision. Astrometry is the craft of tracking where a star sits on the sky and how that spot drifts over time. Gaia does this with micro-arc-second accuracy, revisiting stars again and again across years. That accuracy stacks up. With each pass, it pins down parallax from Earth's orbit, proper motion across the sky, and any extra wiggle that doesn't fit a straight line. Over 1 billion stars get this treatment, so rare motions stand out because Gaia sees the same pattern many times under different angles. Now, young stars are messy. Spots grow and shrink, flares spike, and jets fire. Those can move the photocenter a hair by reshaping the brightness across the stellar surface, and they can twist the timing of measurements. The question is whether a clean orbital signal can punch through that noise floor. The advantage is that gravity plays a long game. A planet's pull repeats with its orbital period and draws a coherent curve, while stellar activity tends to be irregular or tied to rotation timescales and fades when averaged over many epochs. Think of the star and planet as partners locked around a shared balance point. The planet swings wide. The star traces a tiny ellipse that Gaia sees projected on the sky. It's like hearing a metronome under cafe chatter. The clatter is real, but the beat has a fixed tempo and shape. By fitting the ellipse, you extract the orbit's size on the sky, its tilt, and its phase, which together tell you where and when the pull is strongest. Here's the scaling that matters. The size of the wobble grows with the planet-to-star mass ratio and with orbital radius, and it shrinks with distance. Put simply, bigger planets, wider orbits, and closer systems are friendlier targets. Have the distance and the signal doubles. Push the orbit farther out and the wobble widens, though you pay with longer periods that need more years of data to lock down. Take a concrete case. A Jupiter-mass companion at about $5 from a Sun-like star in a region roughly 140 parsecs away will tug the star by tens of microarcsecons on the sky. That sits near Gaia's end-of-mission reach for stable targets. Young stars make the fit harder, but if the orbit is long enough and the sampling is rich, the repeating ellipse can emerge from the noise. Gaia's scanning law is the quiet engine behind this. The spacecraft sweeps the sky along great circles, measuring along skin positions with high precision at many angles. First, you solve for parallax and proper motion. Then you look at the residuals, the leftover deviations that won't sit flat. Acceleration terms point to a companion too slow to map completely, while full multi-year coverage can yield a full orbit. Blend those with the parallax distance, and you convert angular motion into a physical semi-major axis and a dynamical mass. Dust can't mute gravity. Photons scatter in the disk, but the star's center of light shifts because mass is orbiting it, not because the line of sight is clean. That's why this method slips through the fog. Gaia can flag a system where the star leans toward a certain position, angle, and epoch. With that cue, ALMA can check for a gap or a kink in gas velocity at the same radius, and JWST can map warm dust structure. A tug linked to a trench in the disk is a powerful match. From there, a wobble turns into numbers you can use, a mass range, an orbital clock, and a phase marker that tells you when the planet sits behind or beside the star. That timeline lets you catch accretion bursts and disk flows tied to the same orbit, tightening the case that you're watching a world assemble. When light fails in dusty cradles, gravity still speaks. Gaia turns tiny shifts in stellar motion into the first clean hints of worlds being built, giving you a way to see through the haze without chasing glare or heat. That wobble sets the stage for targeted checks of the disk itself. So keep an eye on Gaia candidates that line up with disk gaps or gas kinks. Tell us which systems you think deserve ALMA or JWST time, and which star-forming regions you want unpacked next. Today it's a jitter traced across the sky. Tomorrow it's a mapped network of planetary construction sites.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.